now we're going to define a continuous function. I mean, you know what a continuous function is, right? A continuous function is a function that you can draw without picking your pencil off the paper. That's a very sort of nice logical definition, graphical, kind of pretty, but it's not particularly mathematically rigorous. So now that we know about limits, we can actually define continuity in terms of limits. Continuity is a very important property of functions. We'll see about it quite a lot. So we need to have a good definition for it. And what we're going to use for our definition, this is the definition of continuity at the point x equals a. So I've got some function, and I'm saying that it's continuous at the point x equals a if the limit as x equals a of the function f of x is equal to the value of the function at a. Okay? So this makes some sort of sense as well. As we saw before, when funny things were going on with the limits, there was like a jump, there was a hole, there was some weird stuff going on. What we're saying here is there's no weird stuff going on. Right? My limit, and in fact, that's in this definition. It's right there. But this, if you think about what this definition is saying, it actually has three parts that have to work out for this definition to hold. Okay? So the first thing is that this right-hand side, f of a, is defined. So no holes, right? No holes, no asymptotes. And what I mean by defined, I mean specifically that the point x equals a is in the domain of my function. So I've got a closed circle there. We can make it a closed circle. There's no point in it. Nothing exciting is happening there. Okay? So first of all, the point is defined. The value of the function at the point x equals a is defined. That is what I precisely mean to say. The next thing that happens is that this limit exists, right? Because that's the left-hand side. So the right-hand side of the thing is f of a. The left-hand side of the thing is this limit. And we saw lots of issues with limits. We saw lots of examples where limits didn't exist. But in this case, we need this limit to exist. So we need the left-hand side to exist, we need the right-hand side to exist, and then, of course, we need those sides to equal each other. So even though it looks like a very simple definition, if we break it down, we can see that there's three different ways this definition cannot hold. Okay? So let me draw so that we can kind of explore this thing graphically. Rather than drawing a continuous function, let me draw a function that has some discontinuities, and we can explore what's going on there. And where this fails. Let me see. Let me put some marks here. Oh, it's not straight again. Oh well. Sure, fine. So, let's do this. Let's do this. Let's throw in some asymptote here. Whoop. Let's put in some open circle here. Let's put in some other open circle here. And put in some, that's not shall put it there, let's put it somewhere else. Let's put it here. And some other point there. Okay, so there you have it. There's an example. Okay, so this is kind of all the sort of simple things that could go wrong with this definition. Okay, for example, we can start wherever. We'll start here. Here, this left-hand side doesn't exist, right? Because I've got a jump. The left-hand limit is 2. The right-hand limit is 0. So the limit doesn't exist. So this second, I'm going to get rid of those 3 because it doesn't matter which one is which. So I'm just going to write down what's going on here. At x equals 1, the full limit does not exist. Okay? At x equals 2, well, the limit doesn't exist because it's going off to infinity, but you can see that x equals 2 is not in the domain. So I can say f of 2 does not exist, right? Because it's not defined. So also the limit doesn't exist. So both sides fail, right? Also the limit multiple failures. So at x equals 3, you have f of 3 doesn't exist because I only have an open circle and no closed circle. So that's enough to make this thing discontinuous, even though the limit here exists perfectly well, like the limit is 1, right? And then the last point, we have the same issue. Well, no, we have a different issue. I'm sorry. At this point, at x equals 4, f of 4 exists. It looks like it's 2. And the limit exists. And I think it was also supposed to be 1. Well, let me fix that. So it actually looks like it's at the same level as the point 1. It was supposed to be, right? It's just bad drawing, right? So let's just say that's 1. Okay? But these two aren't the same, right? They are not equal. So at that last point, even though both sides of the equation exist, it's not equal. So we have, well, all those different possibilities. But you can see everywhere else at all other points, if I were to take the limit, it would be, the limit would exist and it would equal the function value. So this function that I drew is continuous at all the points except for these 4. Okay, because I set it up that way. In fact, it's not super important that you remember these, but it might come up, or maybe come up at some other class. So just in general, actually it's not stupid, it's not too unimportant, so maybe I shouldn't have said that. Maybe we should just know this. These are basically 3 different kinds of discontinuities here. These last 2 are considered the same. And so let me give you their names. So at x equals 1, it's called a jump discontinuity. Because there's a jump. Both the left hand and the right hand limits are finite, right? They're both numbers. There's not going off to infinity, but they're just not the same. So a jump discontinuity is the case where left and right limits exist, but aren't equal. At x equals 2, of course, it's infinity, so this is called an infinite discontinuity. As we talked about the vertical asymptote, it's got a vertical asymptote, it's going to be an infinite discontinuity. It doesn't have to be infinite from both sides. If I took this guy, say, over from to here, right, and it was only infinite from one side, that is enough for it to be an infinite discontinuity, okay? As long as going from at least one side, you've got an infinite discontinuity. Some people call this an essential discontinuity. So I'm going to write that as well. Essential discontinuity. Meaning that there's really nothing that can be done about it. There's something really wrong going on in the function. That sine 1 over x where it goes super, super fast, like when it gets closer and closer to 0, that also would count as an essential discontinuity, even though it's not an infinite discontinuity. But pretty much in this class, we'll not, that so much is not such an issue. And then the others, this is called a removable discontinuity. And it's called removable because we can redefine the function to be the same everywhere except that one point, and then you would eliminate that discontinuity, right? So just by redefining one point, I can eliminate that. The difference between that and this, if I wanted to eliminate this, I would have to like move all of these up, or sort of move a whole bunch of them down if I wanted to make it match. So there's some kind of essentialness to that jump discontinuity as well. I can't do anything about that just with one point. I would have to move the whole curve down. Whereas here, I can just fill in these guys, whether it's outside here or whether it's like I just fill this one in by giving it a definition. This one I could just change the definition of one point. So that's why it's called removable. Mostly you'll see we might use this language about, okay, the jump discontinuity, whatever. Okay. Now, what else did I want to do? Oh, I wanted to do one more quick example. I have 2 more examples, so maybe I'll make that a separate video.